Hi, thank you for coming today. I'm Kanji Mori from Fukuoka University, and I'm chairing today's seminar. And today we are happy to invite Dr. Ryo Sawada from the University of Tokyo. He got a PhD degree at Kyoto University in 2020, and after that he moved to the University of Tokyo as a JSPS research fellow, and where he's working now. And he's working on the supernova theory, and in particular, in today's seminar, he's going to tell us about Nikkei 56 problem in supernova explosions. So, Sawada-san, the stage is yours.
Okay, thank you. So thank you for gathering here, and thank you for this opportunity. I'm just recovering from COVID-19, and I'm a little nervous, so little worried. So I hope you will listen to my talk kindly. Thank you. So today I will present the following title. The title say my interests are supernova explosion and 56 nuclear synthesis. I plan to introduce the basic study of 56 nuclear synthesis and the today's main topic, 56 nickel problem. And reference is here. Okay, so first of all, let me explain the what is the supernova explosion. This is sorry. Okay, so okay, sorry. This is just a picture about the astral evolution. At first, dust in the universe gather, and then forms a protostar. At this time, when the star has more than 8 solar masses, the star formed to the iron core during the stellar evolution. And the explosion is caused by the gravitational collapse of the core. This is called the core collapse supernova. Actually, there is another type supernova. For example, which occurs when slightly lighter star undergoing with the binary evolution and occur the type 1A supernova, and more massive star also occurs. The massive more than 100 solar masses star occurs another type supernova explosion. But in this talk, my interest is a core collapse supernova explosion. And I will refer supernova, core collapse supernova explosion as a supernova. And the explosion mechanism of core collapse supernova is as follows. As introduced earlier, star forms the iron core at the end of the stellar evolution. First undergoes the gravitational instability at the center and it is core. And then a gravitational collapse causes a sudden increase of the density of the center and forming a protoneutron star. The recoiled material on the surface of the protoneutron star generate a prompt shock wave. However, this shock wave stored at once and is revived by some kind of the heating mechanism, and then explosion is succeed. Since neutrinos are best candidate for the heating mechanism, so this scenario is called a neutron-driven explosion. So next, I talk about the relation between the radioisotope 56 nickel and the supernova. Today's main topic. Radioactive decay of the 56 nickel is the energy source of the supernova brightness. And hereafter, maybe I refer 56 nickel as a nickel. And 50 nickel is decays this chain, and the emitter positron and gamma ray. This energy adapter ejector. This figure shows the observed point is supernova 1987A, the most famous supernova explosion. And the right curve fitted with the decay heat of the nickel. Also, I will not go into a detail here, but as we can see, amount of but as figures shows, amount of 56 nickel directly affects the brightness of the supernova. This means that the amount of 56 nickel can estimate fairly accurately and easily from the supernova light curve alone, without need for the complex observation, such as the spectroscopy observation. For these supernova, so for this supernova, which can sufficient light curve can be measured, the amount of 56 nickel can be estimated, and statistically, amount of 56 nickel has been estimated from the large enough number of supernova. This is very important for understanding canonical behavior of a supernova. This figure shows a histogram of the number of supernova with the abundance of the 56 nickel on the horizontal axis. The difference in the panel corresponds to the difference in a subgroup of supernova. Without going into detail, it is important to note that the mean and median statistical value are obtained by more than 300 sample of the supernova. This is very enough to discuss the canonical feature. So next, I will discuss how 56 nickel is produced inside the supernova. Okay, so first, to illustrate this feature, for simplify, we use here the parameterizing adiabatic explosion profile. Let us focus on the particular Lagrange particle and assuming the passing shock wave hits that material, and this material explain the peak temperature T0 and peak density rho 0, and then expand in a constant T23 over rho track. This is a isoentropic track. So we assume this temperature density trajectory, and we assume the initial composition is here, and we calculate the nucleosynthesis. This expansion trajectory reproduces general temperature and density trajectory of explosive nucleosynthetic region in the spherical symmetric or multidimensional core collapse supernova explosion. So we calculated this using this trajectory and the nucleosynthesis by the parameterizing peak temperature and the peak density. This figure is a result showing the amount of x-axis is the peak temperature and y-axis is the abundance of the fixed P6 nickel. And we can see a amount of fixed P6 nickel synthesized as a function of peak temperature, and we can see 56 nucleosynthesis results show the nickel is produced rapidly at temperature at peak temperature at more than 5 gigakelvin, regardless the peak density. Color corresponds to the peak density parameters. So this is because the 56 nickel is not synthesized directly, but synthesized the nuclear by the nuclear static equilibrium. At temperature at above 5 gigakelvin, the composition basically follows the nuclear static equilibrium NSE, and this temperature forward and reverse interaction in the main reaction channel proceeded much faster than time scale and time scale of the thermal condition. So this is an NSE. And as temperature decreases rapidly, the reaction rate becomes smaller and the abundance pattern frees out. So in NSE, composition ratio determined so that the Helmholtz free energy is minimized for the nuclear mass function. When thermodynamic conditions are around this temperature, the binding energy per nucleon roughly determines the abundance pattern of NSE, and the environment where the number of proton and neutron are nearly equal. Most abundant isotope in NSE is a 56 nickel. So in supernova explosion, 56 nickel is synthesized in a NSE condition. So let us look at the typical nucleosynthesis model for an actual core-class supernova simulation. This figure shows the abundance distribution of the typical nucleosynthesis model for a 1D core-class supernova. As explained earlier, 56 nickel is mainly produced as in region the shockwave can pass above 5 gigakelvin. So we can see that 56 nickel is mainly synthesized in the innermost region of the explosion at the proton-neutron surface layer. The shock is expanded and at first time, shock keep quite high temperature. So around the proton-neutron star region, 56 nickel is synthesized. So we have sorted out the condition for the 56 nickel synthesis and the environment for the synthesis inside the supernova explosion. So now I will explain how much 56 nickel can be made in the supernova explosion and which property of the supernova explosion it is related to. This can be easily understood as follows. For simplify, 56 nickel is produced by the region where experience peak temperature above 5 gigakelvin. So removing the mass of central proton-neutron star from mass from the mass contained in the region experienced peak temperature above 5 gigakelvin give a roughly estimated amount of 56 nickel. Now, to understand 56 nickel, to understand the nickel synthesis region, we assume the fireball model. For simplify, we assume the post-shock region is a radiation dominant and isothermal, and this region is adiabatic expansion. Then internal energy of AT24 per unit volume is spread to the shock region. And this total energy corresponds to the explosion energy. With the explosion energy now given, consider the radius that can spread at the temperature of 5 gigakelvin. This region will spread linearly to the explosion energy, since the temperature is fixed. Therefore, the mass, the more mass, and furthermore, the more mass is contained in this region, the more 56 nickel is synthesized. So 56 nickel is related to the one is explosion energy. This related to how much extends the 56 nickel synthesis region. And second related to the compactness. This compactness means how much mass is contained in the this region. And indeed, observational and theoretical study confirm that this estimate is not so bad. This figure shows the result of the systematic study of the light curve of type 2 supernova with explosion energy is the horizontal axis and the y-axis is nickel mass. This is observed study. We can confirm there is correlation between explosion energy and nickel synthesis. And here is a more interesting figure. The orange line is the mass of the 56 nickel, and the black line is an indicator of star compactness. More specifically, this indicator suggests the enclosed mass in the normalized certain radius. As you can see, nickel composition correlated with the compactness of the star. So from this point of view, nickel is a very good isotope to systematically estimated from observation of supernova. And moreover, reflect the complex physics of the stellar core. And okay, so this is a very basic topic. And here, I will now discuss the 56 nickel problem in the supernova explosion, which is the main topic today's discussion. The short explanation for this problem is whether modern supernova simulation can synthesize enough nickel or not. And my opinion is no. So I now return once again for the explosion mechanism of supernova explosion. In the neutron-driven explosion scenario, the core gravitationally collapsed and creating the prompt shock wave, and then once stored and revived by some kind of heating mechanism. However, this scenario, especially this point, could not reproduced by the simulation. In particular, it is unclear whether this scenario can reproduce the enough explosion energy considered to observationally typical. It's a 10 to 51 erg. So this is one of the big issue in astrophysics. And I briefly summarize the recent state-of-art multi-simulation. The recent so state-of-art simulation employs the multi-D and full Boltzmann and full Boltzmann neutron transport and the neutron GR effect, etc. And these figure are simulation result for separate group. This x-axis is the time and the vertical axis is the energy. And looking, now we look at the time growth of the explosion energy. The unit of the vertical axis is a bit complicated, but they are normalized by typical value. Therefore, simulation is successful when it leads to the 1. As these results show, most of simulation first, this group could not reach the unit value, but some good slope model will be reached to the 1 for more simulation time. And in this group, they are succeeded in reproducing the typical explosion energy using the 7-second simulation. So these results show, the most of the simulation do not reach the sufficient explosion energy, but if not all. And these simulations now suggest the very slow explosion than the previous thoughted. But that this explosion energy time scale. So here we define the explosion time scale up to the 10 to 51 erg called T grow. These simulations suggest the T grow is more than 1 second. But these explosion timescale have any effect to observational behavior of supernova explosion. This was the motivation of my own research. So this is my research talk. my motivation is that does the explosion time scale affect the nucleosynthesis or not? So if affects the nucleosynthesis, we can constrain the explosion time scale. This means from observation, there is a if affected from observation, the good time scale is there. And we do a 1D height dynamics and a nucleosynthesis simulation with the explosion time scale as a parameter. And the explosion model is here. So this is our assumption of the explosion model. In my assumption, shock wave is artificially produced by injecting thermal energy directly into the press supernova star. End of it is stellar evolution. And injected time evolution is like here. So first inject linearly, and we are stopped injecting thermal energy. So therefore, where shock wave is produced is depend on the injection position. In other words, this is one of the parameters. We want to find the sufficiently robust upper limit of the nickel production. So we choose the position well inside. And detailed simulation setup is like here. We use the 3 progenitor model, and we use the BL code, and hydrodynamics is Newtonian, and EOS we use the Helmholtz. And first we calculate the small network calculation, and the post process we calculate the detailed nuclear reaction network. And result is here. X-axis is time scale of the explosion, and the y-axis is synthesized nickel. So left side corresponds to the instant explosion model, and the right side corresponds to the slow explosion model. So it is a little bit difficult to read this figure. So later I talk. This plot is the amount of the synthesized 56 nickel, and not all of it will be ejected. So the figure shows that maximum amount of 56 nickel can be ejected in each model is plotted. In other words, to reproduce the observation, plot must be above the typical value. And we use the typical value 0.07 solar. This is the typical value from the nearby supernova. And we can see the decreasing tendency with the time scale is longer. And in slow explosion, synthesized nickel is suppressed. And in this region, all of model could not couldn't the above observed line. So these models are unfavorable from the observation. Why this trend is occur? This is simply we can understand very simply. For as before, we consider the fireball model. So shock is a radiation dominant and the isothermal and adiabatic expansion. And +1, and we assume the constant velocity expansion. So this relation can be written the temperature as the time, as a function of the time. And when explosion energy is sufficient is instantaneous, then explosion energy have a 10 to 51 erg from explosion energy have a 10 to 51 erg from the initial setup. So in the instantaneous explosion, it first is a very high temperature, and this is cooling, adiabatic cooling expansion. But when taking into account the growth time scale of the explosion energy, then shock have a time to get the enough energy. So synthesize the time can be synthesized the nickel is shorter than instant explosion model. This tendency can be see the also can be see our hydrodynamical result. This figure x-axis shows the mass coordinate, and y-axis is a temperature, and the line suggests the evolution of the peak temperature. Red line suggests the instant explosion model, and magenta and blue line suggests the slow explosion model. As we can see, compared to instant explosion model, a slow model is suppressed. The temperature of slow explosion model is suppressed. And this tendency is affected for the nuclear synthesis. This top panel is the instant model, and the slow panel is a slow, the bottom panel is a slow explosion model. And the red line corresponds to the 56 nickel. In an instant explosion model, we can synthesize sufficient nickel, but slow explosion model, we couldn't synthesize. So this is a reason why slow time scale is suppress the nickel synthesis. And this is the our study. But some point our study some point have some question our study is having. Our first question is nickel amount actually not reproduced in the state of art simulation? And the short answer is this is no. Recent some model in the state of the art simulation have succeeded in reproducing the typical mass of 0.07 nickel. And this figure shows the nuclear synthesis result for the small network in the study presented earlier, in which explosion energy reached to the default value in the 7-second simulation. We do not deny this result by any means, but this is just one of the energetic success story among the various large timescale computational study. We are then arguing that it is unclear whether the model with a longer explosion timescale can reproduce sufficient amount of nickel as a canonical nature is now still unclear. So, and the second problem is the uncertainty of the observed value to be compared. For example, we use 0.707 solar as a typical value for the nearby supernova. However, according to the histogram shown at the beginning of the talk, the median of three subgroups are around or above this value. But there is a subgroup that clearly lower median value. So how much value is correct is unclear. So we therefore re-estimate the nickel abundance from the supernova, our own observation using unified methods. And type 1b supernova are known as the explode from helium core star, and type 1c supernova from a carbon core star. So we then estimate the matching core by adding fixed 1.4 solar to the ejector mass estimate from observation. And we perform the same nucleosynthesis calculation and timescale comparison for each using estimated core. This is the result. For each time scale, the percentage of supernova can be reproduced. The observation is shown. As shown, as this figure shown, we conclude that the difficulty of few 10% of the observation can be explained by non-standard supernova explosion. But the time scale for that reproduce less than 50%, less than 50%, difficult to adopt the standard explosion time scale. So we as we assume the time scale 0.1 second, we can explain the most of the all supernova, but when we assume the time scale as 1 second, we couldn't explain the more than half of the supernova. So this is from this study, we checked the observational uncertainty. So this is a final topic and a little bit confusing and difficult talk. So just recently, the Imasheva et al. Pointed out the most obvious question to the 56 nickel problem. Their argument is as follows. We have injected explosion energy directly into the star. However, a modern explosion model scenario star contracted well before explosion. Moreover, position of shock wave revival is different from our assumed injected position. This figure is the x-axis is the time and y-axis is the radius, and these lines correspond to the mass shell. So this and this figure suggests the and this red line suggests the shock wave. So this figure suggests that before the supernova exploded, the star is enough constructed. So they are first confirm that same trends by the same trend observed with exactly same setup with our simulation, and then argued that these correlated trends disappear when the take into account the contraction that before the explosion, and inject position is changed. These decreasing trends are disappeared. So the argument is our result may come from the ignoring the gravitational contraction before the explosion. So, say further discussion inevitable depends on the parameter of explosion model. So we are currently revisiting the this issue with a more realistic and self-consistent explosion model. In this model, only parameter is a neutrino luminosity, and everything else is self-solving from this equation. And this figure shows a mass shell until the shock mass shell, and the blue line suggests the shock line. As we can see in this model, we can consider the gravitational contraction before the explosion. And this dotted line indicates the non-explosion model. In this figure, we can confirm the behavior of the mass shell up to arrival of the shock is independent of the explosion model. It's quite matched. And this is a very interesting result. This result shows the time evolution of the shock from the model, and neutron luminosity is 3 times 10 to 52, and 5 times and 7 times and 9 times. So it's a different neutron luminosity. This corresponds to the different energy growth rate. So as we find very interestingly in the all model and the and in each model, time evolution of shock are shown in the color line where shock satisfies the above 5 gigakelvin, and the black dash line corresponds to the shock decrease less than 5 gigakelvin. This is very interesting. We find in all model the shock near the 10 to shock near the 5 gigakelvin is near dotted mass shell coordinate. This corresponds to the enclosed mass of 1.65, and this trend is almost universal independence progenitor model. So we can conclude this nickel problem. First, we find the 56 nickel is depend on the explosion time scale, and rapid is a very good enough nickel is synthesized, but slow model couldn't synthesize. However, Imashba suggests the taking into account the gravitational contraction, the slow model also also synthesize enough nickel, but we find the new picture of 56 nickel. Indeed, outermost radius is insensitive to the explosion dynamics, but innermost region is sensitive to explosion nature. So it is a universal trend. Rapid explosion can synthesize enough nickel, but slow explosion model couldn't synthesize enough nickel mass. So this is that's all. Oh, thank you.
Thank you for the great talk, Sawada-san. So now it's time for questions. So please raise your hand if you have any questions or